Okay, so thank you for the introduction, Ian. Thank you everyone for turning up. Hopefully I'm going to convince you that crystals are something that physicists want to think about, work with, study, and take a bit of an interest in. It has been the basis of my career as I've travelled around the world and met some fantastic people, been to some amazing places, and it's led to many opportunities I would never have imagined while being in high school. I barely imagined going to university, never mind going on to becoming a lecturer. So this is kind of the general public perception of crystals at the moment. Crystal meth, Breaking Bad, that's fantastic. Oh yeah, that's so cool. Yes, somewhat. It's a step forward from where we were a few years before that, which was, oh, crystal healing, that's so cool. I can put them on my chakra, yeah, that's great. Definitely had a couple of discussions in pubs and sort of some nefarious relationships based on that. But it's more crystals are fantastic, and they are the basis for so much of what we do in physics. And actually in everyday life, you encounter crystals, and so much of matter itself is based on crystals. Things that you probably don't even realize are crystalline in nature. By us studying them, it leads to unveiling why these properties exist and how they come to be. What I'll do next is play a little video from a guy called Max Perutz. It's kind of an overview of his Nobel Prize winning speech, and it sort of explains a bit more quickly how crystals are such a fantastic field to study.
Why water boils at 100 degrees and methane at minus 161. Why blood is red and grass is green. Why diamond is hard and wax soft. Why glaciers flow and iron gets hard when you hammer it. The answers to all these problems have come from structural analysis. That's how the Nobel Prize winner Max Perutz summed up X-ray crystallography. Never heard of it? Don't worry, not many people have. Yet it's arguably one of the greatest innovations of the 20th century. 28 Nobel Prizes have been awarded to projects related to crystallography, and the very first of those is where it all began. It's now 100 years since, following early work by Max von Laue, the first structures were determined by father and son team William and Lawrence Bragg. In 1913, they fired a narrow beam of X-rays at a humble salt crystal and photographed the diffraction pattern as the crystals split the beam into many rays. Lawrence soon realized that this pattern held the clues to the atomic structure of the crystal itself. The equation he developed, Bragg's law, made it possible to work out how the spots in the diffraction pattern are related to the specific arrangement of atoms in the crystal. 2 years on, and the Braggs were awarded the Nobel Prize. Impressive stuff. Not only that, the Braggs mentored a dream team of crystallographers who went on to work out the structures of a huge range of molecules. From Kathleen Lonsdale, J.D. Bernal, and Dorothy Hodgkin, to David Phillips, John Kendrew, and Max Perutz. Remember him? Plus, Rosalind Franklin and others even helped map the structure of DNA, probably the most famous result of X-ray crystallography. Today, the work hasn't stopped. Crystallography remains the foremost technique for working out the atomic structures of almost anything, which is very useful for finding out why things behave the way they do. From the metallic structure of the blades of a jet turbine, to the immune system fighting off viruses. Turns out, Max was right. Modern crystallographers are doing exactly the same thing as the Braggs, just at a larger scale, with more sophisticated mathematical methods and more impressive machines. Crystallography is even reaching beyond our planet. The Curiosity rover is now performing X-ray diffraction analysis of the soil on Mars. But there's plenty of unfinished business back on Earth. There are still many thousands of complex molecules to look at, and a lot more questions to answer.
So that's basically why it's worthwhile looking at crystals because it can explain so many things. The Braggs themselves were extremely innovative in many, many ways. They invented the method to let us see atoms and how they're arranged in crystals. They actually had invented X-rays. Well, didn't invent X-rays, but they invented the first ever medical use of X-rays. And what happened was, so the father, William Bragg, when his son was about 4 or 5, they were living in Adelaide, Australia, and then Lawrence actually fell over and broke his arm. And being the good physicist that he was, he said, "Oh, I've just heard about these things called X-rays. Let's have a look." And so he literally took his son and stuck him in front of an X-ray source and took the first ever medical image of a broken arm of his son. Not sure how that would go with the health and safety people these days, but yeah, that's what they did. As explained, they won the Nobel Prize for being able to see atoms, and they also pioneered women in science. As you may have noticed, Kathleen Longsdale, Dorothy Hodgkin, and many others were all direct descendants, or either worked directly with the Braggs or with their PhD students who then went on to become supervisors. And during the 1900s, especially during the First World War, 60 to 70% of the people in their labs were female. And that has stuck to this day. It is still true within the field of crystallography. When I was working X-ray crystallography, I would go to these conferences and it'd be 50% women. I then changed fields into electron microscopy at one point, and I was just like, where did all the ladies go? It was pretty bad. It then dropped to about a quarter, that statistic that David was talking about. But we're working on improving that, and it definitely has. We began to redress that balance in the last few years. So the Braggs are an extremely impressive group of people. So this is why crystals are so, roughly 85% of everything that's solid is a crystal. So if we want to understand matter, solid matter, we have to understand how to look at crystals. And so where do we encounter these? Well, LCDs, or liquid crystal displays. So it's crystalline switching within the display that allows you to get all these vivid colors and display these great screens. Salt, sugar, all the electronics, they're all based on crystalline materials. How we modify these crystalline materials is what gives us our electronic properties. So without crystals, modern day life basically doesn't exist. If you've got a quartz-based watch, that's a little quartz crystal which is vibrating back and forward. So maybe quartz, with the addition of some of the new smartwatches, maybe more watches are becoming more reliant on the silicon-based technologies than they are the quartz-based technologies, but still, for the past 40, 50 years, quartz-based timing is the way that most things have been done. Even in biology, crystals are everywhere. Your teeth are essentially calcite crystals. Bones are calcite crystals held together by collagen. Insulin stores in the pancreas as a crystal. And so the understanding how insulin crystals dissolve and reform within the body is extremely important. It's actually one of the areas that I work on, is understanding how these small microcrystals dissolve in the body and what we call polymorph, which type of arrangement within the crystal the insulin has within the body is extremely important. It controls all of its physical properties. One form of insulin will dissolve very quickly. Another form will dissolve extremely slowly. And so with 25% of all people in the Western world suffering from diabetes, understanding how this works is extraordinarily important in medical science. Another area is inflammation. In certain diseases, uric crystals, so uric acid basically builds up into these small crystals in the joints and will cause extreme pain. Understanding how this happens and how can we block it from happening can lead to massive health benefits for a huge number of elderly people within our population. Anyone suffering from gout or related diseases, this is exactly the problem you're suffering from. Your eyes are actually crystalline. So it's actually a series of small crystals that build up the lens in your eye. So the proteins come together in these crystalline arrays and form the lens in your eye, and as they flex back and forward is how you focus your eye, with a bit of help from muscles round about. Glaucoma and related diseases are essentially these crystals going wrong. They're aggregating in ways that shouldn't happen, and this is what leads to many sort of diseases of the eye. So studying how these things occur is of massive importance to your everyday life if you have a problem with your eyesight. Some of the biggest crystals in the world are on the scales of tens of meters. This is a gypsum crystals that was recently discovered around about 2005 in a cave in Mexico. There was literally some guys looking for some lead crystals, and they were just mining away, and they literally just chipping away with a small hammer, like handheld. And then they broke through into this cavern and got the shock of their life. And it's like an alien world. So crystals can be on massive scales. Anything metal is also crystalline. You often hear the line that there's no straight lines in nature. That's just not true. Bismuth crystals make these beautiful, colourful crystals of very defined facets. These pyrite iron sulfide crystals, often found around about volcanoes, form these beautiful, perfect prisms. And you can just find them lying on the ground. They're quite impressive. So if someone says to you, you don't find straight lines in nature, it's just not true. Crystals are everywhere, and they form lots of straight lines. So I want to introduce a bit about Ireland's contribution to the world of crystallography. So the building just opposite this one, which you'll probably pass through later today if you go on the tour, is named after Kathleen Longsdale, this woman here. She was born just outside of Dublin. She discovered the structure of benzene. Okay, it's a pretty simple molecule. Why is that so revolutionary? Well, the Braggs, who won the Nobel Prize and discovered the whole subject, actually proposed the structure of benzene first, except they said it had a puckered ring, where the atoms were in a sort of chair conformation, it's often called. And Kathleen Longsdale, just fresh out of her PhD, said, "You're wrong." She actually went to the Braggs and said, "You're wrong. The structure of benzene is a nice flat ring, and you've got delocalized electrons above and below this ring, and that's why you see these magical properties." And the Braggs were very humble about it, and they said, "Okay, let's investigate more." And they came back 2 years later and said, "You know what, you're right," which made Kathleen Longsdale a bit of a superstar. It's not any old student or young new scientist who can walk up to a Nobel Prize winner and go, "You're wrong." She also wrote a thing called International Tables while being a pacifist in jail during the Second World War. International Tables is like the Bible for crystallography. Anytime you need to know anything, you refer to this table. Her influence in this subject is huge. And she was also the first to apply Fourier methods, basically take mathematical techniques to help solve these crystal structures, to understand where the atoms are within these crystals. Another guy who was mentioned in that video earlier was J.D. Bernal. Bernal was an amazing character. He pioneered protein crystallography. He sort of said, well, we can take these proteins and we can crystallize them together and then begin to understand their atomic structure. This is actually him looking at an early model of the structure of water. He also discovered and solved the structure of cholesterol. 6 of his students and postdocs went on to win Nobel Prizes. He himself wouldn't put his name on their papers. Even though he contributed to it, he was just a magnanimous individual. He was often known as the sage of science because he just had such a broad knowledge. He was born up the road here in Neenah. He also planned the D-Day landings. His contribution was huge. He worked out the beaches, where to go, why not to go there, how to go there. If you should get the chance, read the book on his life. His biography is just outstanding. You don't hear much about him in terms of the D-Day landings because he was a committed Marxist and communist. And that didn't go down too well with our American friends across the pond. So they kind of, I'll just forget about this guy. He did win the Medal of Lenin, but did not win the Nobel Prize, which many people feel he should have done for his massive contributions to a huge number of subjects. So Irish scientists have had a huge role in crystallography and its whole course. So what is this crystallography business? Well, basically, this video kicks in, it's scattering X-rays, electrons, or neutrons off of atoms. And if you just have a single row of them, then you get these lines in reciprocal space. So we often think in reciprocal space. So we're in 3D space right now. We've got inverse space, and this is how we look at things. It's much easier than just physically watching stuff, because the wavelength of light doesn't allow us to access the atoms directly. We have to use X-rays, and it's very difficult to focus X-rays, so we look at the scattered properties. And as you can see, as you move the lattice around, it changes size in an inverse way. So as you stretch the atoms apart, these dots get closer together. As you push them together, they get further apart. As you introduce different weights of atoms, you'll see that the intensities change with time. We can even use this to look at liquids, which should be next. Yeah. So if the liquids are all moving about, looking at these intensities of how this all scatters still gives us information we can relate back to what is going on in even liquids. So we can extrapolate from our understanding of how the solids work into the liquid phase. So the knowledge of how X-rays and X-ray crystallography work have allowed us to do all that. Like people, it's their crystals, it's their imperfections which make them interesting. Like a pure lattice of a crystal has a certain array of properties, but if we can introduce imperfections to that, we can take atoms out, we can take vacancies, we can substitute some, we can put in interstitial atoms between odd places on the lattice. We can put in smaller atoms, bigger atoms. This gives it a whole new set of properties. And how these things behave is how things like hardening steel works. So just taking a regular piece of steel, before you've tempered it, it's not very good for structural work. Like this building probably would fall down. Understanding how these interstitials and these defects play a role in both electronics and metals, this controls our everyday life. So how do we look at these? Now it's very hard because, like we showed, or like I mentioned earlier, we can't look directly at the atoms using light. So how we do it is using an electron microscope. And how the electron microscope works is we take a small beam of electrons down a evacuated tube, and we have a series of magnetic lenses. So we have the source up here, and from there we pull out some electrons, and we have a very, very thin sample. The great thing about electrons is they interact, or they're easy to manipulate using magnets. The bad thing about electrons is that they interact very strongly with the matter that we're trying to look at. So the samples have to be extraordinarily thin. So we can push the electrons through this very thin foil of the material we're trying to look at, and then we can image directly the positions of the atoms. And we can see the relative spacings in the lattice. We can look for these interstitials, these defects, begin to understand why they have the properties that they have. Another way of doing this is the scanning electron microscope, where we have a slightly different arrangement of the lenses, and then we take a very fine beam and we raster it back and forward. So like the old CRT TVs that used to have sort of back in the 80s, and they would scan across the crystal that you're trying to look at. On top of this, what we can do is we can look at the properties of some of those interactions. So as these electrons are traveling at 300 kilovolts, so about 3/4 the speed of light, and they hit off the crystal, and it causes the atoms to vibrate and do all sorts of other processes, and they output X-rays. We can look at the spectra of those X-rays and analyze what each individual atom is. As the electrons interact with the crystal, we can then put it through a prism equivalent to a light prism, so basically a triangle of a wedge of glass equivalent, and it scatters, and we can then look at the electron loss for each of the electrons in the or for each of the atoms, and then that tells us all sorts of things about the bonding between each of its surrounding atoms. We can begin to understand the intimate way in which it relates to all the atoms which surround it, and we can actually tell the chemical species of each one. We can differentiate between iron 2+ and iron 3+, which under certain circumstances is extremely important. You take hemoglobin, if you've got hemoglobin 2 or 2+ or 3+ state, it depends if the oxygen is bound or not. And so that can make incredibly important in understanding the whole mechanisms of how your biology works, why breathing is a good thing, etc. So here in UL, we've just managed to get one of these new fancy microscopes installed, and if you go on the tour later this afternoon, I'll have the pleasure of showing you this. Here is a small overview of the building of this microscope. So this is the microscope sitting in the basement. This Lego version of the microscope over here, you can actually download the instructions and build it for yourself from websites in UL. I think the physics department website here has a link to that. So you can actually build the model yourself and let your students see. There's an electron microscope, and we have like the equivalent of the EELS spectrometer on the bottom. We have like the little EDX detector. It's all in there. The reason it's in that big box is because it needs to be protected from acoustic and thermal noise in the room. Because you're looking at individual atoms, the pressure wave from your body walking across the room is enough to disturb the measurement. So we have to have it in a very safe, special environment. So what's all this TEM good for? Well, if the classic methods of powder diffraction fail, then we can look at one of the individual crystallites in a powder. So if you take a salt crystal, you can take one of those tiny salt crystals and look at it in the microscope. Another way physicists tend to look at these crystalline structures in things called free electron lasers. There's only about 3 or 4 of these in the world. They cost several billion each to build. And getting time and access to these things is a bit of a nightmare. But for just a few million, which is cheap by comparison, but still more than I have on me, we can give access to these in many places around the world, and we're very lucky here in UL to have a machine which can do more or less what this thing can do. If your sample's just too small to look at in general, if the powder diffraction methods have limitations on the size of the crystals that they look at. So we can go down to individual atoms, so we don't have a limit on the crystalline size that we can observe. And if your sample's polyphasic, so if there's just too many crystals of different types within the thing that you're trying to look at, then because we're looking at individual crystals one by one, this isn't a problem, whereas for many of the other methods, it can be. So what do we look at? Well, one of the things we looked at recently was a metal oxide for the semiconductor industry. And what we're able to do, this is actually a lattice of atoms, and these lighter atoms in between are these it looks kind of grayish, but these are actually all individual atoms. Using the Xray spectra which come off of these, we can actually assign what atom types are in the sample, and we can overlay them and say, okay, this is exactly what this is. So we've gone from a black and white image to a color image to understand the complete crystal. And so what types of things do we look at other than that? 2D materials have become the massive trend since the Nobel Prize for graphene in 2010. We're actually lucky to have Ursel Bangert here, who was the first ever person to look at these 2D materials in the TEM, and I'm lucky enough to work with her. We now look at a huge array of these 2D materials. They're probably going to be the next generation of materials which the electronics industry is going to use. They're very much aimed also at making quantum computers work. Some of the properties that these things have lend themselves quite nicely to quantum computing devices. So these things are probably going to power the next wave of computing advances. So nanocrystals come in all shapes and sizes. They cover just about every subject you can imagine. We look at basically all of these things with other researchers here at UL. I'll give you a quick overview of graphene. So you start with a big crystal of graphite. You then exfoliate it, which basically just means taking sellotape, more or less, and you just keep going until you have a little bit on a piece of tape. We then transfer that onto a TEM grid. We then zoom in. You can see this object here is the flake that we're trying to look at. We zoom in again. The flakes are here. It's not so obvious to see. This is zoomed in right into the center of one of these holes where the flake is lying across it. And this area here, the graphene itself is actually in the dark holes. Because it's so thin, it sits in amongst all the muck. And if we zoom in again on that area, which looks essentially dark, we can actually see the crystal lattice of these 2D materials. And then we can begin to look at the defects, the properties that provides us with, and begin to understand how we can design and make materials for the next generation of, in this case, computers, or it can actually be water filters. The graphene-based water filters are being made for making the most pure water possible. And with that, I'd like to say thank you for your attention.